Hi everyone, welcome to this video on compile design. In this video, we are going to discuss particularly on the intermediate languages used in compile design. Let us dive into this video. What is intermediate code generation? In the analysis synthesis model of compilation, the front end analyzes the source program and creates an intermediate representation. From the phases of compiler, we understood that the source program is converted into the target program by converting in between the intermediate code. The intermediate code is neither in the form of the source code nor in the form of the target code. That is the property held by the intermediate code. The purpose for the intermediate code generation is to smoothen or simplify the process of code generation. So from the picture, we very well understand that the source program is fed into the parser. I think from the lexical to the parser is communicated, from the parser to the static checker called semantic analysis, and further to the fourth phase called intermediate code generation, which actually generates the intermediate code, and finally to the final set of phases called code generation, where the set of phases till the yellow color box called the intermediate code generation is called as the front end, whereas the last part is called as the back end, where the front end generates the intermediate code while the back end generates the target code from the intermediate code. Why? What are the intermediate languages we have? So we have high level representations as syntax trees, which is suitable for static type checking, and we have the low level representation of intermediate languages as three address codes, which are suitable for register allocation and instruction selection. So variants of syntax trees, which is the high level intermediate language form. So it can be represented as syntax tree or it can be represented as a DAG, where particularly the DAG, directed acyclic graph, is suitable to identify the common sub-expressions. Let us take this example: a plus a star b minus c plus b minus c star d, where we have the common expression as b minus c, and how DAG helps in tackling this particular common sub-expression or the entire expression. And this is the DAG for expression specified in the previous slide. Uh, in the normal syntax trees, every node is created and every parent will be created with its new children for the respective operation performed. But in the case of DAG, it is not happening. The DAG will utilize the existing nodes and will use them as parent or child whenever required, and that is why it is able to minimize the number of nodes a syntax tree has, and it can also identify where the relations are and where the common sub-expressions are. From this DAG, we can very well understand that there is a cyclic path here. Usually, a tree will not have cycle, a graph will have a cycle. But this property of tree called DAG will have cycle, which indicates there is a dependency of expressions, and that is why DAG is said to identify the common sub expressions, and that is the relations, obviously. What is three address code? As we understood from the very first topic of phases of compilers, three address code is an intermediate language which contains exactly three addresses and two operators. Actually, it should be one. In addition to the regular operation performed, it has the assignment operation by default. So there are two operators and there are three operands that can be available in a three address code, and that is why it is called three. A maximum of three addresses can be used, three variable names can be used in this intermediate code or intermediate language. Any larger expression should be divided into such three addresses so that the machine code generation is easier. Look at this example x plus y star 2, where the preference goes to star when compared to plus. So y star z is performed first and the sub answer is added with the value called x or variable called x and assigned to the temporary variable called t2. Because we divide the entire expression into pieces, there is a need for introducing temporary variables, and those are called t1, t2, etc. in our terminologies. So this is the DAG and intermediate code, that is the 3 address code representation for the same statement we discussed in the previous slides, and which means two different representation of intermediate languages. One is the high level representation called DAG, another one is the low level representation called 3 address code. We particularly move with 3 address code because it is easier to translate it into machine language, because register allocation and other processes are easier with 3 address code. And these are the different forms of 3 address codes. It can be used to represent addresses such a way that names, constants, any compiler generated temporary can be used to represent. And any form of instructions can also be represented by 3 address codes, like binary assignments, binary assignments involving binary operations. Binary operators assigned with a value, unary operation assigned with a value, etc., etc., etc. Jumps, conditional jumps, unconditional jumps, etc. can be the probable types of instructions available in 3 address. And the procedure calls, returns, indexed copy, which is involving the concept of arrays, address and pointer assignments involving the principles of pointers, are all different examples of 3 address codes which can be encountered in a program. So this is the actual content of the topic. 3 representations of the instructions, or 3 different implementations of the intermediate languages as quadruples, triples and indirect triples. We very well know quad means 4, triples means 3, and hence the answers are. Let us understand from the next set of slides. We understood that every 3 address code will have a maximum of 3 addresses, 3 operands and 1 operator, and hence we use quadruple as one of the implementations involving 4 fields: operator, first argument, second argument and result. And let us understand from the example given below, a equal to b star minus c plus b star minus c. Again we have a common sub expression. This entire expression involves a unary operation also called minus c, and binary operation called star as well as plus. Let us understand how they are implemented using quadruple. So this is the quadruple implementation of the intermediate code called 3 address code, where we have 4 fields: operator, argument 1, argument 2 and result. Let us take the first statement, t1 equals minus c. t1 is the result represented in column 4. The operator applied is unary minus, represented in the column 1 as operator, and the argument applied to this u minus is the operand c. And there is no argument to, because it is merely the unary operation. And this is stored in the index 0, and similarly other indices are. Let us take for an example t5, which involves the addition of t2 and t4. The operator used is plus, the argument 1 is t2, argument 2 is t4, and the result is stored in t5. And this is how the quadruple is implemented. That is, the 3 address statements are transformed into an implementation called quadruple and stored in the memory. And temporary names must be entered into the symbol table as they are created. That is the usual property that we have. Triples, on the other hand, as the name implies, we need 3 fields: operator, argument 1, argument 2, where the result column is ignored. Let us understand how this is tackled. From this slide, we can very well understand the result column is ignored, and how somewhere or the other we need to fetch where the result is, because it might be used as the input or argument to the subsequent set of intermediate codes. And from this slide we can understand that the argument 2 for the second instruction called T2 equal to B star T1 is implemented as the index 1 using the operator star, using the argument 1 as B and using the argument 2 as index 0. Rather referring to the temporary name, the triples directly refer to the index where the actual value is stored. It refers to the record rather referring to the temporary name. The reference to the temporary or the need for temporary variable is ignored completely in terms of triples. Temporary names are not entered into the symbol table in this case of implementation. Triples has a benefit over quadruples. So it is used for in terms of optimizing compilers, instructions are moved around. So moving instructions for quadruples doesn't change the other instructions, but whereas in the case of triples it might affect, and we will see how to overcome it. So indirect triples is a list of pointers to the triples. We try to optimize the implementation so that it is also suitable for optimization purposes as well, where the reordering of the instructions is essential. In the case of intermediate code, we can apply indirect triples concept. So indirect triples has two different tables. In addition to the triples table, we maintain a separate table to represent the set of indices. In the case where the statements are to be reordered, it is not necessary for the triples to refer to the indices or change the indices again, because the indices are indexed separately and they are referred separately in the table triples. Triples is added, or it is given an assistance with a pointer, and that is why it is called indirect triples, so that reordering is not a problem in case of triples, indirect triples. So let us compare in terms of indirection, the suitability to optimization and space. Quadruples, there is no indirection involved. It lends well to the optimization because the rearrangement is easier. There is no references, indirect references applied. Rearranging will not affect the optimization. The space is not that optimal because we use 4 fields. Whereas triples is good in terms of space compared to triples, but it is not that suitable for optimization because the rearrangement of statements or records will affect the answers. So it is not that well suitable for optimization. However, there is an indirection presence that we know very well. In case of indirect triples, indirection is defaultly present, the name itself states. It lends well to the optimization because rearrangement will not affect the answers or flow. We need not have any other task to be done. But whereas it requires more space because there is a triple and there is an indirect triple. Both go hand in hand with indirect triples. So the amount of memory required is much more when compared to the other two implementations. So these are the three different implementations of intermediate languages. Hope this video makes you understand better the concepts of implementation of intermediate codes. Let us meet in the next video. Thank you.